Hello everyone, this is Ming. In this video, we are going to walk through the Feedforward neural network notebook. This is basically after we sign in for Databricks cloud environment, and we have already introduced the basic operation, the basic user interface for Databricks. In this section, we are going to import the notebook for Feedforward neural network part of the course. Let's come to our course homepage. In this course homepage, we have a list of links, notebook links. The first one we're going to import to look at it is the Feedforward neural network notebook. Let's copy the link address, copy the link location. And we're going to use the location to import notebook to your own account. Now let's go back to Databricks Community Edition, and here for the cluster, there is one that is up and running, test 01. And if in your environment you do not have a cluster up and running, you can create a cluster. It only takes about 1 minute. Once we have a cluster up and running, now let's import the notebook for Feedforward neural network. We can click on the home icon on the left. It is going to show the notebooks that is already under my account. At the space, the white space here, right click, it's going to show create. That is what we did to create a notebook. Import is to import a notebook somebody else has already created, or a notebook you created somewhere in some other locations in your local computer, for example. We can import from files or import from URL. And in this case, we're going to import from URL. After you click, it's going to show the box. Now let's paste the address we copied from the course homepage. So this is basically the Feedforward neural network notebook that we're going to go through. Okay, click import. Now, this particular notebook is actually imported to your own Databricks environment. So basically, it is your notebook. It is actually our notebook. The default language is R. It is in your environment, and you can write on top of the cluster you created. For me, the cluster actually need to be attached. On the top left corner of the notebook, there's a cluster detached indicator here, and click this drop-down menu. Is you're going to see all the available clusters that is up and running. In this particular case, we have test 01. We click on that. Basically, now this notebook is going to run on top of test 01. Let's click the Run All button on the top, in the middle of the top. It is going to run all the scripts from the first cell to the bottom. And because it is going to spend some time to download and install required R libraries, let's let it up and running, and I'm going to go through all the details here. As we mentioned earlier, we can have a markdown cell. So the first cell is actually a markdown cell. We see their headers, their bullet point, etc. Those are pure text. If you double click on that cell, you can see there's a magic word of %MD at the first line to indicate that particular cell is a markdown cell. The second cell is actually a markdown cell as well. So in the Feedforward neural network notebook, we are going to use R Keras library to create a feed-forward neural network model. Before we can run your feed a neural network model, we have to download the needed library. So the needed library is actually Keras, and it can be downloaded directly using the install.package function, and it is going to download all the dependency for Keras as well. As you can see, they're also downloading all different kind of libraries, packages that are needed. And this is actually done. It took around 1 minute to download quite a lot of libraries here. So after the library has been downloaded, we need to load the library and run the install_Keras function to set up the backend of the computation. And because the Keras library is actually based on Python, so it has to download the needed Python files as well. But for us, we do not need to care too much about the backend of the Keras library. We actually is going to be focused more on the front end of using Keras library functions to create a neural network model. Now, let's look at dataset. The MNIST dataset, as we mentioned earlier, it is a relatively small dataset for handwritten digits. 0 to 9, 10 digits handwritten, and the original image of the handwritten digit has been pre-processed in a 28 by 28 resolution grayscale. So this MNIST dataset is included in the Keras library. Once we loaded the Keras library, we can easily get the dataset by calling the dataset_MNIST function. So then the MNIST R object contains all the data. Now let's look at the structure of the MNIST R object. It is a list of two: the training and the test. The training by its own is a list two as well. X and Y. Y is basically the value of the handwritten digit, one of the values between 0 and 9. The X is the input. It has a 28 by 28. It's the input image. And for the training data, we have 60,000 rows. For the testing data, it has 10,000 rows. And the X, again, is 28 by 28 matrix. Y is just for each row, there's only one value, one of the 10 digits. So this is all pre-processed, ready for us to use. Then we extract the training data, the testing data, X and Y, into separated R object. We can actually plot one of the images to look at it by using the code segment here. So this is for image 28 in the training data, and it has a digit of 3. So that's basically convert the 28 by 28 matrix into a grayscale image. If we look at the 28 by 28 matrix, we can see that those are numbers, integers between 0 and 255. The grayscale. Now let's look at it, the feed-forward neural network, and how we can use Keras functions to build up a deep neural network model. But before we build a neural network model, we do need some data pre-processing. In deep learning and typical machine learning algorithms, we usually do the scaling as well as reshape. In this particular example, we're not going to treat the image as a image of 28 by 28 matrix. We are going to actually convert this 28 by 28 matrix into one vector of 784, which is 28 by 28. So we actually lose the spatial correlation in the image. We're going to treat each pixel independent of each other. It's become 784 independent features in, uh, in the training data. So to do that, we call the array underscore reshape function for the x training and x train and x underscore test data frame. So basically, we reshape them into, for each observation, for each digit, it's going to be one row and 784 columns, which is corresponding to the 28 by 28 pixel. And once we reshape them, and we also scale them. So because those are all integers between 0 and 255, once we divided each pixel, each and every pixel by 255, is becoming a number between 0 and 1. This is basically the structure of the training and testing data for X features after the reshape and the scaling. So as you can see, for the training data, it's become a 60,000 row and 784 column data frame. That is basically our very typical machine learning model training data. Each row is an observation, each column is a feature. Now we have 784 features in the data set. For the response variable, which is basically one of the 10 digits, for carries, because the digits label is treated as categorical variable, and then we actually is going to use the two categorical function to convert the digit integer 0 to 9 into a 10-dimensional dummy variable. So it's like the one-hot encoding. So basically for the response, instead of only one column, now we have 10 columns. And the corresponding column is going to be 1 if the digit is related to that. Otherwise, all other columns become 0. So those 10 columns, they're going to take either value 0 or 1. It's a dummy encoding or one-hot encoding. After we finish this pre-processing, now we're all ready to feed a deep learning model. The first step is actually define a neural network structure. To define neural network structure is straightforward. So we first create a placeholder for the model by calling the carries underscore model underscore sequence function. And then it's becoming our object, the placeholder, to contain the neural network structure. Now we can create the first layer. The first layer is a dense layer. Basically, it's fully connected. Each neuron is actually fully connected to the 784 input features. In the first layer, we have 256 neurons. Basically, that's the units. And the activation function is rectified linear unit. And the input shape is 784, which is basically our input number of columns for each observation. And it is only needed for the first layer, the input shape. So once the first layer 256 neurons are added with activation function ReLU, and then we add another layer for dropout. Dropout is basically used to reduce overfitting, and the dropout rate is defined as 40%, 0.4 for the first layer. Then we create a second layer which has 128 neurons and the same ReLU activation function. The dropout rate for the second layer is 30%. Now let's add a third layer with 64 neurons, again activation function ReLU, with dropout rate 30%. The last layer is actually going to connect to the output. We do have a 10-column dummy output, or the Y labels. So we're going to use unit is going to equal to number of columns in the output, 10 in this particular case, and the activation function is softmax, which is the typical one for the multi-class classification problem. So this basically create the model structure for a 3-layer neural network. We can look at the details of this network structure by using the summary function here. It's actually going to tell us the number of neurons, number of parameters for each layer, and the total number of parameters. As you can see, even for we only have 60,000 training data, but the number of total parameters is 242,000. It is very typical. We have more model parameters than number of training data. For a neural network models. So that's why dropout are used quite a lot to reduce overfitting. After the neural network model has been defined, we need to compile it because we still need to define what is the loss function and what is the optimizer and what is the metrics we want to track during the model feeding stage. So this is done by compile. By using the compile function, we define what is the loss function, what is the optimizer to use, and what is the metrics we track during the model feeding stage. Okay, after the model is compiled, then we can do the model feeding by the feed function. In the feed function, we actually identify what is the training data X, what is the training data Y, and how many epochs to run for the training, and what is the mini batch size, number of observations that we're going to actually update the model parameters. And the validation split percentage is actually going to automatically divide the training data into 2 pieces, training and validation, and we're going to report the performance, the accuracy for the training data and the validation data to see whether we are in the overfitting range or not. All right, so as you can see here, it is running for the first epoch, etc., etc. The accuracy, the loss, they're all kind of saved for each epoch, for each mini batch actually. And as you can see, the accuracy actually increased pretty fast. Very soon it's actually reached more than 97% of accuracy in the data. So now, once it's finished, take a little while. It's less than 1 minute. It's less than 1 minute to run this particular model feeding. And then once the model has been fed, we can look at it. What is actually the output? The output it include the metrics for each epoch, and for the training and validation. So we can actually plot the details. Here we see on the top graph, it is the loss versus number of epochs. The bottom graph is actually accuracy versus the accuracy versus epochs. So the training data and validation data, we can see the accuracy is all goes up. And when the validation training accuracy is pretty much the same, is the indication that's kind of like at the edge of overfitting. Once the model is fitted, we can actually evaluate the testing data to see the real performance, because the testing data is a brand new data, the model never seen before. We use the evaluate function. It returns the accuracy. It is 97.9%. It's not bad for this particular data set. We can predict, and using the predict underscore class function to actually look at it. What is the prediction? And we know the grand truth, and this is a predicted class. Last, we can actually check a few misclassified images using the code below. It is straightforward, and this is one of the misclassified images. I don't know what this image is about. Maybe 2, maybe 7, maybe 1. So all possibilities. Let's look at image for digit 7. So the writer originally wanted this digit to be 7, but this particular algorithm is wrongly predicted this as 1. So even human may not predict this particular digit correctly. All right. So this is pretty much the end of this notebook. Because we lose the spatial image correlation information, so there are definitely room for the for the performance. And actually, for image, if we want to consider the pixels, the relationship between pixels, and definitely a convolutional neural network is a much better choice. We're going to cover in the next video.